Okay, hello everybody. Good morning, good evening. This is the last day of our CAR 2022, and it's a place for me to introduce Professor Elżbieta Sidorowicz. Ella, for friend, is one of the most important mathematicians in her university, and she has been my host in several times in Poland. So really it's a very honor for me to be here, and you will be our invited speaker in this occasion. I just like to say that for me, Hela is a silent person, but if you need her, you can find her. So thank you very much, Ella.
Thank you very much for your nice introduction, and thank you for inviting me for this very nice meeting. It's a great pleasure to link with you. So I'm going to talk about the connection in digraphs. So let's. It's okay? You see my screen?
Yes, but you need to put full screen.
Maybe.
Again. Again, no problem.
It's okay?
No, we cannot see. Okay, now it's okay.
Okay, yeah. So I'm gonna talk about the proper connection in the graph, and let's start with some annotation. Okay, so the first. Okay, so by V. Oh no. By V of D, we denote the set of vertices of digraph, and by A of D, the set of arcs. An arc is a pair of two vertices. The first vertex of the pair we call tail of the arc, and the last vertex is a head of the tail. And if the arc join U and V, then E is an out arc of U, and E is an in arc of V. In degree of the vertex is the number of in arcs, and out degree is the number of out arcs. Okay, so directed path, I will call path for short. So every time if I say path, I think about directed path. So this is not a path. This is not a path. And similarly for the cycle, directed cycle, I will call for short cycle. And so here is example of cycle. And a digraph is strong connected if every ordered pair of vertices is connected by a path. So strongly connected digraph is called strong. So cycle is strong, however, path is not strong. And no definition related with the proper connection. So the first, we say that our colored path is properly connected if it does not contain any two adjacent arcs with the same color. And if we have an arc-colored digraph, then we say that it is properly connected if between every pair of vertices there is a properly colored path. And in such a case, we say that the corresponding coloring is properly connected coloring. Okay, and we generally are interested in the smallest number of color. So by the PC of D, we denote the proper connection number. This means the minimum number of colors needed to color arcs in such that we obtain the properly connected digraph. And we can observe that in order to admit an arc coloring which makes it properly connected, a digraph must be strong. Here is example of the properly connected digraph. If we choose any two vertices, then always you can find the properly colored path which join these two vertices. And also from this vertex to this vertex, we can find properly connected, properly colored path. So if we check this, so we can observe that every two vertices are connected by properly colored path. But we can say more about this digraph. If we consider this cycle which is outside, which contains all vertices, then we can observe that we can find a properly colored path which going through the arc of this cycle. So, so this means then the arc which are inside the cycle, we can color it with any color, arbitrary, and the digraph still be properly connected. So, and of course, this works for, so such a property works for every arc-colored digraph. So if we have a properly connected digraph, then we can add some new arcs, color them arbitrary, and the result digraph is still properly connected. The concept of the proper connection was introduced by these persons in 2012, and this paper inspired many new results on the proper connection numbers or graphs. So this, in this paper, these authors introduced the concept of proper connection for graphs. And also it inspired considering some variants of proper connection number, like strong proper connection and also vertex version. And the next, in 2016, this author introduced the notation for the digraphs. So they define the proper connections in digraphs. And since then, many paper appears about the proper connection in digraphs. It was considered a version in which vertices in the stat arcs are colored, so the vertex version. And then the proper colored path is a path in which adjacent vertices have different colors. Also, it was considered proper connection in total colored digraphs. In such a case, the path is properly colored if it contains neither two adjacent arcs with the same color, neither nor two adjacent vertices with the same color, nor a vertex with the same color. But in our talk, I will consider only arc version. So I always color arcs. So I always consider arc coloring. In the first paper, when the notation was introduced, it was proved the following theorem, that if digraph is strong, then the proper connection number is at most 3. So we can observe that the only digraphs with the proper connection equal to 1 are complete digraphs. Complete digraphs, this means digraph in which every pair of vertices is adjacent by arcs. Here is example of complete digraphs on 4 vertices. So we can see that only such a digraph has the proper connection number equal to 1. So since if the digraph is strong, that the question is whether the proper connection is equal to 2 or 3. So we have two possibilities. However, it appears that the problem of deciding that whether the proper connection number is equal to for a given digraph is amply complete. So it is a hard problem. From this result, it follows that it is interesting to give a characterization of the digraphs with the proper connection number equals to 2, or give a sufficient condition for digraph to have the proper connection equals to 2. And the family of such digraphs are bipartite digraphs, strong bipartite digraphs. Maybe recall the definition of bipartite digraph. So it is such a digraph in which the set of vertices we can divide it into two subsets, two disjoint subsets, such that every arc has its tail and its head in different part of partition. So for strong bipartite digraphs, we have the proper connection equal to 2, of course, except K2, this means complete digraph on two vertices, because for this digraph, the proper connection number is 1. And here is the idea how we can color arcs to obtain the proper connected digraph. So all the arcs with the tail in the set V1 and the head in the set V2 we color with the color red, and all arcs with the tail in V2 and the head in V1 we color with blue. In such a coloring, every path is proper colored. So the coloring must be properly connected. As we observed before, if we add an arc to strongly connected digraph and color them arbitrarily, then we result in proper connected digraph. This means if in our digraph we choose spanning strong subdigraph and color the arcs in such a way that we have the properly connected digraph, the remaining arcs of the digraph we can color arbitrarily. So in other words, we can say that if H is a spanning subdigraph of D and H is strong, then the proper connection number of the digraph is at most the proper connection of H. So from this and the previous result, we have that if G has a spanning strong bipartite subdigraph, then the proper connection number is at most 2. So this means to find the good coloring, which the coloring with the smallest number of colors with results in the proper connected digraph, it's enough to find a good spanning strong subdigraph. If we find a bipartite, then we are done, because we have we use only 2 colors, and we know that the 2 is the small possible color if it is not complete by digraph. Of course, not every digraph with the proper connection number equals to 2 has a spanning strong bipartite subdigraph. We generalized the theorem for bipartite digraphs in the following way. We prove that if D is a strong digraph and if it has partition on 2 disjoint sets V1, partition of vertex set on 2 disjoint sets V1 and V2, such that the first set induces a strong bipartite digraph and the second set is an independent set. Then also the strong connection number is at most, the proper connection number is at most 2. And of course, if we find in the digraph the spanning strong subdigraph has these properties, then also the proper connection number of this digraph is at most 2. Another family with the proper connection number equals to 2 are tournaments. A digraph is a tournament if any 2 vertices are joined by exactly 1 arc. This means if we consider the underlying graph on this digraph, then it is complete graph. Okay, and these authors prove that if a tournament is strong and has at least 4 vertices, then proper connection number is equal to 2. If tournament has 3 vertices, then it must be a cycle. So we need 3 colors. And if it has 2 vertices, then it is not strong. So we must have at least 4 vertices. And how we can prove this result, this theorem? First, we can observe that every strong tournament has Hamiltonian cycle. It is no result that every strong tournament has Hamiltonian cycle. So if the number of vertices of tournament is even, so we have the even Hamiltonian cycle. So we can color the arcs of this cycle with 2 colors, remaining arcs which are not in this Hamiltonian cycle, we can color arbitrary, and digraph will be still stronger, will be still properly connected. So the only case which can be proved is that is the case when the tournament has even number of vertices. But this author also proved that it is also true. So again, if we have a tournament and it is strong, then it has a Hamiltonian cycle. If it has even number of vertices, then we can color the arcs of this cycle with 2 colors. And going through the arcs of cycle, we always can find properly colored path. However, if a tournament has even number of vertices, then to find we must color the to find the properly colored path. We must also use the arc which are inside the cycle. We must also use these arcs which are inside the cycles. And this the proof says that we can always find such a coloring of this arc inside and arcs of cycle that 2 colors are enough. So this result inspired our study because we can wonder how many arcs which are inside this cycle, how many holes can we remove from tournament without increasing proper connection number to 3. Of course, in even tournaments, we can delete all arcs, but in the odd tournaments, some arcs must stay. This problem we can reformulate in the following way: which Hamiltonian digraphs had the proper connection numbers equal to 2? And we focus on such a problem. We find some sufficient condition for Hamiltonian digraphs to have the proper connection number equal to 2. But before I present this result, I need some definition. So let's see this be the cycle on n vertices. Let's denote these vertices in this way. A chord of a cycle is an arc which joins 2 non-consecutive vertices of this cycle. And the chord is even if the path going through the cycle is even. If the length of the path going through the cycle is even, otherwise the chord is off. So on this picture, the red chord is even because the length of this path is even. It has 4 arcs, so the length is 4 of this path. So the red chord is even, the blue one is odd. And we prove that if D is a Hamiltonian digraph and C is a Hamiltonian cycle of this digraph, then if every vertex of D is a tile of even chord, then the proper connection number is at most 2. And if in this theorem we can replace the tile but the head. So if every vertex is a head of an even chord, then always the proper connection is at most 2. And from this theorem follows that if we have the Hamiltonian digraph and C is a Hamiltonian cycle, and if C contains only even chords, and for each vertex in degree is at most 2, then proper connection is at most 2. And it is also true when we replace the in degree by out degree. We expect that this result remains true when the word even, so when we even chords replaced by odd chords. So we conject that this is also true, that if in the Hamiltonian cycle, if we have digraph which is a Hamiltonian, if the Hamiltonian cycle contains only odd chords and every vertex has in degree at most 2, then the proper connection number is also at most 2. And also we think that it will be true for the out degree at most 2. Okay. Next we consider circulant digraphs, and here is the definition of circulant digraph. So let S be a subset of integers from 1 to n minus 1. A circular digraph C and S is a digraph with such a set of vertices with n vertices, and the vertices we denote in this way: B0, B1, Bn minus 1. And we join 2 vertices is the difference between indexes is equal to S, and S is an integer from the set S. Here is an example of a circulant digraph on 7 vertices when the set S contains 1 and 3. So what means that 1 is in the set S? This means that we have a Hamiltonian cycle because every 2 vertices which are in which index is different by 1 can be joined by an arc. So always if in the set S is 1, this means it is a Hamiltonian cycle. And next we have 3. This means we join 2 vertices which indexes differ by 3. So this means 2 vertices which are in distance 3, which are in distance 3 going through the cycle. So other words, with add chord, which length is 3. Okay, and we prove the following, that if we that every circular digraph, which such that the set S contains two integers and it contains one. This means every circular digraph which is Hamiltonian has the proper connection number at most 2. So we have a Hamiltonian circular digraph, and additionally there is additionally one integer in S, so it must contain some holes. To prove this result, first we can observe that if n is even, so if our digraph has even number of vertices, so it is Hamiltonian digraph with even number of vertices, so we can color the arcs of Hamiltonian cycle with 2 colors, and we are done. So for circular digraphs of even order, it is easy. Next, we can observe that if we have odd number of vertices and still one is in S, this means our digraph is Hamiltonian. And in the set S, in the set S is integer, even integer, then this result will follow, and no, I recall the slide with our show before, then the result, it follows from this theorem, because then every vertex is a tile of an even chord, because then chords are even, and from each vertex we start with one chord. So to finish the proof of this theorem, it is enough to prove the case when n is even. So if we have n is odd, so if we have odd number of vertices, and if the set S are only odd numbers, and we prove this by this lemma, we prove that one odd number is enough. So if the set S is 1 and k, which is odd, then also the proper connection number is at most 2, and it is equal to, because in such a case we will not result with the complete digraph. So if n and k are odd, then the circular digraph n1k has the proper connection equals to 2. Okay. So we generally focus on Hamiltonian digraphs and give sufficient condition for Hamiltonian digraph to have the proper connection number equals to 2. And we can ask the question, what difficult is the problem of deciding whether the Hamiltonian digraph had the proper connection number equals to 2? What is the complexity of deciding whether a Hamiltonian digraph D satisfies that the proper connection number of the digraph is equal to 2? We know that from previous result that if we for all digraph, it is complete problem. Is this problem remains complete for Hamiltonian digraphs? Okay. As we observed before, in order to admit a properly connected arc coloring, a digraph must be strong. So we decide to extend the notation of proper arc coloring on all digraphs, not necessarily connected. So we define properly quasi-connected digraph. So an arc colored digraph is properly quasi-connected if between every ordered pair of vertices in which are connected by path in our digraph, there is a properly connected path. So in this case, we say that corresponding arc coloring is properly quasi-connected coloring. And again, we are interested in the smallest number of colors, so the parameter related with such coloring we call the proper quasi-connection number, and we denote it in this way. Here you have example. The path is not strong. However, we can consider the proper quasi-connected coloring of path, and we can color it with two colors. So the proper quasi-connected number of path is equal to 2. And also here graph. This graph is not strong. This graph is not strong because as we can see that we cannot from any vertex of this part, we cannot go to any vertex of this part. But we can color this arc in such a way that if there exists a path between two vertices, then also exists a proper colored path. So for example, we can choose this vertex and this vertex. These vertex are adjacent by path, and we can find proper colored path. If we choose these two vertices, of course, from this vertex to this vertex, there is no path, so there is also not proper colored path. However, from this one to this one, we can find something like here, proper colored path. Okay, and one more example. This digraph is also properly quasi-connected. All arcs are colored with one color. As we can see, this digraph is transitive. What means that digraph is transitive? Here is a definition. If for every pair of arcs x, y, and y, z in the such that x is different from z, there is the arcs x, z is also in D. So if we find our digraph x, y arc, y, z arc, then also must be this part, this arc from x to z. And from the definition, we have the following properties of transitive digraphs. So in transitive digraph, if there is xy path, then also there is an arc xy. So from this property follows that every transitive digraph has the proper connection name number equal to 1. Connection number equal to 1. Okay, so let's compare these two parameters. So for the proper connection number is equal to 1 if digraph is complete. Proper quasi-connection number is equal to 1 if and only if D is transitive. If D is a strong digraph, then these two parameters are equal. Proper connection number is equal to proper quasi-connection number. We know that proper connection number is at most 3. However, we prove that the proper quasi-connection number can be arbitrarily large. I show this later. No, I only want to remark about this and some other properties of the proper quasi-connection. So let's consider the family of unilateral digraphs. The digraph is unilateral if for every pair of vertices x and y, either x is reachable from y or y is reachable from x or both. So for every pair of vertices, there must be a path from one vertex to another or from another to the one. And for path is unilateral. However, this digraph is not, because if we consider these two vertices, x and y, there is no path from x to y, and there is no path from y to x. So this one is not unilateral. We prove that if D is unilateral, the proper quasi-connection number is at most 3. And then, because every unilateral, every Hamiltonian digraph is unilateral, then we obtain the following: that if G has a Hamiltonian path, then its proper quasi-connection number is at most 3. Because if D has it can be proved that if D has Hamiltonian path, then it must be unilateral. And then we know that every tournament has Hamiltonian path. Strong tournaments has Hamiltonian cycle, and if tournament is not strong, then it must contain Hamiltonian path. And for those we obtain that for every tournament, the proper quasi-connection number also is at most 3. Of course, if the digraph is not strong, we very often use the notation of strong component of digraph. What it is? A strong component of digraph is a maximal induced subgraph which is strong. So if a digraph is not strong, we are looking for the maximal subdigraph which are strong. And now next, the strong components we contracting to the single vertices. And the resulting digraph we call the strong component digraph. Here is an example. So we have a digraph, and here is one strong component. So it will be 1. Here is another 1, 2, 3, and 4. So it has 4 strong components. And now we're contracting strong components to a single vertex. Of course, when parallel arcs appears, then we delay them. So this vertex corresponds to this component, this one to this, to this, and this one to this. So this is a strong component digraph. And what we can observe that we can bounded the proper connection, the proper quasi connection number of digraph which is not strong by the proper connection, proper quasi connection number of it, a digraph of strong components. And so we have, and also we must add 3. We know that each strong component can be colored with 3 colors, so it can see that if we color the arcs using the colors which we use in the strong, strong component digraph, we can obtain the coloring of all digraphs. And we can observe that, and we know that the strong component digraph is acyclic. It always acyclic graph. So according to this, is interesting to consider the connected quasi coloring of acyclic digraphs. And we prove that for every integer, there is acyclic digraph D such that the proper quasi-connection number is equal to K. So the proper quasi-connection number of acyclic digraphs can be arbitrarily large. And I want to prove, of course, the proof of this theorem is by construction. I will show only the maybe a sketch of construction for K equal to 4. How we can construct the acyclic digraph with the proper quasi connection number equal to 4. So first we start with such a digraph. The proper connection number of this digraph is 3, because let's try to color the arcs of this digraph. And we show that we must use here 2 colors. So first arc we can color arbitrarily. Next, this arc must be colored with other color, because this is the only path from this vertex to this one. This arc can be colored with 1, but we cannot use the same color. And this arc must be colored with 2, but because again, this is the only path. And here, this we can color 1, 2, 1, 2, and here must be put 1. So this arc must be colored with 3. So we can observe that 3 color, we are not able to color this diagram with 2 colors. We must use 3 colors. And then we will construct in some steps the diagram with the proper quasi-connection number equal to 4. So first we construct the digraph D1 in such a way that we take 3 copies. We take 3 copies on this previous graph, and next here we add new vertices, and these vertices is A up to 3, because for every subset of 3 vertices, we form one vertex which is dominated by these 3 vertices. So for every 3 vertices, each from other subgraph, we add one vertex. Next, we take 2 copies of D1, and again, for every part, for every set of 2 vertices, we add new vertex, which is dominated by these 2 vertices. And then we construct D3. We take 2 copies D2, and again, for every subset of 2 vertices, we add one vertex, which is dominated by these 2 vertices. And next, finally, the G4, we take 3 copies of D3, and for every subset of 3 vertices, each from one set, we add one vertex, which is dominated by these 2 vertices, and next we add additionally one more arc. And finally, this D4 is a digraph with needs 4 colors. Maybe I skip some slide. I do not explain why, because I ran out the time. Okay. So as what we can observe from this construction, that to construct a diagram with 4 vertices, we need to construct a diagram with the proper quasi-connection number equal 4. We need more. It is a large graph. It has a lot of vertices. And similar construction will generalize from arbitrary K. So generally, our diagrams has a lot of vertices, and we wonder if exists the diagram with smaller number of vertices, and appears that it is not the case. Why? Because we prove the following theorem. We prove that if this is an acyclic diagram with a proper quasi-connection number equal K, then it must contain path of the length 2 up K minus 1 plus 1. This means it must contain a path of the of the large length, so the number of the vertices must be large. Of course, in our construction, probably the number of I'm sure that the number of vertices is not optimal. We can find smaller, but not very small. Okay. And next we prove that for a given integer K and a given diagram, deciding whether the proper quasi-connection number is equal to K is NP complete problem. And we also find some upper bounds on the proper connection numbers. But first, I again introduce some notation. Recall that the source of the vertex is the source if the integer of the vertex is 0. So source is a vertex which is incident only without arcs. There is no in arcs to the vertex V, and we define source partition of vertices. And we define it for the acyclic diagrams. So a partition, V1 from V of the vertices of the diagram is source partition if V1 is the set of source of D, and Vi is the set of the source of in a diagram D minus V1 sum up to Vi minus 1. So maybe on this picture. So V1 is the set of the source. Next, we delay the source in our digraph, and in the remaining part, we are looking for the source. And again, we delete the vertices in V2, in V1, in V2, and in the remaining part we are looking for source. And in V3 are all the source of the digraphs which doesn't contain these vertices from the set V1 and V2. And we can see that such partition is uniquely determined for an acyclic digraph, and we prove that if this acyclic digraph and has source partition into P sets, and if P is at most 2 up K, then the proper connection number is at most K. And on the other way, we can reformulate a little bit in this theorem in this way. So if D is an acyclic digraph and it has partition into source partition into P sets, then the proper quasi-connection number is at most minimum K, such that 2 up K is greater or equal P. So we are looking for the smallest K, such that we can bound that P by 2 sub K. And then this is upper bound for the proper quasi-connection number. And of course, for in the case when digraph is not acyclic, we add 3. Okay. And next, we can also observe that we can bound the proper quasi-connection number by the chromatic number, or what it means the chromatic number of the digraph. The chromatic number of the digraph is the chromatic number of its underlying graph. Underlying graph, then we omit arcs. From arcs we make edges, and then the chromatic, we obtain graph, and the chromatic number of this graph is the chromatic number of the digraph. And we can see that the proper quasi-connection number of the digraph is the chromatic number of graph D by the chromatic number of D minus 1. And here is an example how we can explain this observation. We know that if the chromatic number of digraph is K, then we can partite the vertices of digraph into K independent subsets. So here is example for 3. We can partite vertices on 3 independent sets, and then all arcs with the head with the tie in this set and head in this set we can with one color, on arcs with the tie in this set and head in this set in another. Sorry. And again, we use other than these 2 colors for coloring these arcs, other 2 colors for coloring this arc, and so on. And we see that we can, in such a coloring, we can use a chromatic number multiplied by chromatic number minus 1 color. So we have an upper bound as a function of chromatic number. Of course, we can also observe that the chromatic number, the upper bound for the chromatic number is the maximum degree of maximum degree of digraph, and again by the maximum degree of the digraph, I denote the maximum degree of its underlying graph. So, and we know that if the underlying graph is neither cycle nor complete graph, then we can chromatic number upper bounded by the maximum degree of the digraph. So we have the following upper bound. So if the underlying graph of D is not a cycle, then the proper quasi-connection number is at most maximum degree of D by maximum degree minus 1. So we have upper bound as a function of the maximum degree. Of course, you can wonder, we can ask about the better function, because as we see that it is so a trivial upper bound. Can we find the better upper bound as a function of the maximum degree? And and also we can ask about the lower bound as a function of the maximum degree. As we observe and in our construction of construction of digraphs which large the proper connection, the proper quasi-connection number, the graphs always has a large maximum degree. So as we observed far 4, it was a large graph and it has large maximum degree. So we can ask the following question. Find a lower bound on the proper quasi-connection number as a function of the maximum degree. We think that if degree is small, then we cannot force a lot of colors in digraph. So I would like to finish my talk with such a problem. So thank you for your attention. It's all what I.
Okay, thank you very much, Ella. Nice talk. I think it was very clear. So I don't know if somebody has a question, comment. Okay,
Yes, I have a question.
Yes.
Yes. Very nice talk. I like so much. Do you know any example of the do you talk in the end of the talk? In the end of the talk, do you talk about the chromatic number with the other number? Do you know any example that the bone is?
No, probably no, probably it's it is there are not such diagrams that we can find the better upper bound. So probably, yeah, no, I know example bipartite, because for bipartite it will be 2.
Okay.
So but for a bigger chromatic number, I think that this mode it's too high. We can find it's not tied. We can find the better upper bound.
And when you talk about the connection unilateral connection, who you work the coloring?
Sorry, I
yes.
You are asking about unilateral digraph, yeah? And
yes.
Sorry, I don't understand your question.
Yeah. No, only no. I confused. Sorry. Yes. Thanks.
Okay. Vinicia say thanks a lot for the talk. And I don't know if we have some comments. I have a question. I don't know if has more than a question is I was thinking about your problem. You use in your first results the condition will be Hamiltonian digraph. So I was thinking it will be interesting to think about hypo-Hamiltonians. It means that you quit any vertex. You have not Hamiltonian, but if you quit any vertex, then you have a Hamiltonian.
Yeah.
And its family was studied a lot, and there is very nice constructions.
It will be interesting, yeah.
Okay, if you like, I can
didn't
send you.
consider such a case. Thank you, because I think that it's a good idea, because I wonder, I wonder which family I can consider more, because for diagram, it's not very large known families. It's very good. Thank you.
Okay, if you like, I can send you information. There is a very nice paper of Thomasen. There is a big construction for this hypo-Hamiltonian was very studied in the past. And I think it's very interesting
very nice
to put attention of this family. So I will send you by email information. You're welcome. So, okay, I think we don't have any questions now on YouTube, but if we receive any question, we write you and we send you.
Thank you
So-
for your question and comments.
Okay, so thanks a lot to Ella for his nice talk, and we will continue in 3 minutes with our last talk in this card.